Chapter 22, condensations and alpha substitutions of carbonyl compounds. Those carbonyl compounds that we're going to see in this chapter, we will basically learn alpha carbon chemistry, whether it's alkylation, acylation, or halogenation, or even reacting with other carbonyl structures. The very first slide I would like to start with is the acidity of those hydrogens, and that's slide number 60. If we look at that list of pKa, it's very useful to be familiar with those numbers, the fact that we have a pKa chart available to us. So when you look at the water acidity, it's 15.7. When you go from alcohol or water, which is about 16 or so, to a ketone, the alpha carbon has an acidic hydrogen that has a pKa of 20. And if that carbon hydrogen has a carbonyl next to it, that will increase the acidity. You could see that if I go from a ketone to a diketone, the alpha carbon right there, it goes to 9, from 20 all the way to 9. And every single 0.1, that's a 10 times more acidic. So that's how acidic it is when you deal with a structure like this. An ester alpha carbon, because of the donating effect of the alkoxy, it makes that hydrogen less acidic. You could see the pKa goes up to 24. The lower the pKa, the more acidic the hydrogen is. Now, that's a diketone. The reason why this alpha hydrogen has much more acidic than the regular monoketone, that is because of the conjugate base. The conjugate base, it's much more stabilized compared to the monoketone. You could think of that alpha carbon, once it gets deprotonated, it's going to give you an anion. Here's one, and it could delocalize to the right to form an enolate. So you basically make a C double bond C O minus. That's the second resonance. Or that negative could go to the left, and that's your third resonance. While this one, if you delocalize that negative charge, it gives you a second resonance form, that's the enolate. So you have 2 resonance forms versus 3 resonance forms of the conjugate base. The more resonance form the conjugate base does have, the more stable it is. And the more stable it is, the weaker it is as a base. And we know that the weaker the base, the stronger the corresponding acid or the conjugate acid. So that's important to keep in mind. Why it is the diketone alpha carbon is much more acidic than a monoketone. If I have a ketoester, the alpha carbon still is acidic, but it's not as acidic as a diketone alpha carbon. You can see it is about 11. If you have a diester, the alpha carbon right there is going to be much more acidic than the other carbon hydrogens in the structure, of course, because of the stabilization of the conjugate base. The pKa is around 13. So it's very important to keep in mind that those alpha carbons acidity, in the case if we're dealing with reactions that do have one equivalent of the base, we know which hydrogen to pick, because the most acidic hydrogen is the first one to go when you have a base looking for a hydrogen to deprotonate. So those structures, once they those structures that have alpha carbon hydrogen, once they get deprotonated, they will be giving you what we call an enolate. The hydrogen, once it's being picked up, that CH bond is going to go back to the carbon, and that gives you the carbanion. And this carbanion will be stabilized with a resonance form, this negative charge making a C double bond C, picking up or pushing out the C double bond O to make a negative charge. And that's basically the enolate. So whether you look at this structure or that, the same exact term will be used, which is the enolate ion. And whether you use this one or the other to react with an electrophile, it doesn't matter. If you decide to use the carbanion, then it will the arrow pushing will go from there to attack the electrophile. If you decide to use this enolate, then the O minus makes a double bond, and then the C double bond C, that's where the electron density goes out of to attack the electrophile. All of these alpha carbon hydrogens, once they get deprotonated, that's where the attack is going to be from on the electrophile. And that's where you see the alpha carbon attached to the electrophile. Now, that electrophile can be an alkyl halide, can be an acyl halide, can be a halogen. And that's what we're going to see in the following slides. Now, this alpha carbon, once you form the enolate, it is strong enough to attack a carbonyl structure, and that's the nucleophilic addition, basically. So you have the negative charge attacking a carbonyl to push up a pi bond to give you a tetrahedral intermediate, and that O minus now it grabs a hydrogen from the solvent to give you a hydroxy ketone, basically, at the end. And this hydroxy happen to be on the carbon the number 3 from the carbonyl, which is the beta carbon. And that's important to keep in mind. The beta hydroxy carbonyl compound, it's a reaction that we're going to learn later on. The main point is to form the enolate first before it attacks another carbonyl structure. And that's called condensation of an enolate with an aldehyde or a ketone. Same pathway. If we have the enolate, it can also attack a carbonyl of an ester, and that will be a condensation. Why would it be called a condensation? Because you are basically pushing out an alkoxy group. So this is it may look like a substitution, but it's actually more correct to call it a condensation reaction. So this enolate attacks the carbonyl carbon, kicking off the enolate, the alkoxy, once it goes through the tetrahedral intermediate. And at the end, you end up making a beta keto ester, beta keto ester. So that's the substitution product in here will be actually a diketone. Instead of having an ester to start with, you end up making that carbonyl attached to the carbon of the enolate. We've seen the tautomerism phenomena in the reactions of alkynes when we do hydroboration oxidation and when we do oxymercuration demercuration. Tautomerism is about having a keto form being in equilibrium with the enol form. And this equilibrium, and again, I said tautomerism, not resonance. This is not a phenomena that happens because of resonance. What's happening in here, that you have basically a tautomerism, and that's more of an isomerization, not resonance. So the alpha carbon, it basically goes through an abstraction of the medium, and the medium, once it grabs that hydrogen, forms a double bond, and that CO minus grabs the hydrogen back from the medium. So you end up making a keto and enol form. The keto form happened to be a much more stable molecule. And however, this tautomerism, if it takes place in the presence of an electrophile, this enol can actually be consumed in that reaction, whether it's alkylation, acylation, or halogenation. We're going to see that. Yes, it's a slower process compared to generating an enolate. Remember, when I say enolate, that means I'm forming a C minus. That's an enolate. But here I see it's an enol. The enol will be less nucleophilic, less reactive to compared to an enolate. So it's important to keep in mind the reactivity. Faster reaction obviously will be when we have an enolate to react with an electrophile. Here's another example. We could see the equilibrium lies toward the keto form rather than the enol form. So the base catalyzed enolate formation is using a hydroxide as an example, or later on we're going to see amides are also used to grab a hydrogen from the alpha carbon, and that carbon ion will delocalize to form an enolate. So this enolate basically grabs the hydrogen from the medium and gives you the enol. So you have an equilibrium, goes back and forth between the keto and enol, as we say. So this could be utilized in those reactions that we're going to see in this chapter. And we're going to see here also the acid catalyzed tautomerism. So the carbonyl in this case will be protonated first. So the base catalyzed, we see the deprotonation of the alpha carbon. But the acid catalyzed, we have the carbonyl oxygen being protonated first. And once that happens, then this CH bond, you can see here the resonance form of this structure, that this CH bond being picked up by the solvent, water in this case, and it delocalizes to form a C double bond OH. So that's the enol form. So whether you have the acid catalyzed or the base catalyzed, you end up generating a C double bond CO, H, or C double bond CO minus that will act as a nucleophile in those reactions of alkylation, acylation, or halogenation. Something we also seen that the enol keto form can go through racemization. What is that supposed to mean? What it means when you start with a stereo-defined stereocenter, like this structure, for example, it's an R configuration structure. In the presence of H plus or OH minus, you end up making an enolate or an enol. This enol, it kills the stereochemistry of that carbon. So you end up basically making now the enol that's going to go back to the keto form, but that keto form will make a racemic mixture. So when you have a stereo-defined alpha carbon and you run alpha carbon chemistry, there is a big chance that this stereo-defined carbon will lose its stereochemistry. And that's an example we see here to prove that. So that's called racemization, starting with a stereo-defined structure, ending up with a racemic mixture of the same exact structure because of the enol keto formation, which is tautomerism. So we see in the acidity how it is important actually to keep in mind that those alpha carbon, such as ketone alpha carbon, will have an acidity of pKa of around 20. So when you have an alkoxide picking up a hydrogen, that's going to give you the enolate, major and minor. You are required to draw both of them. Just keep in mind the major one will be the one that's going to have the negative charge on the most electronegative atom, which is the oxygen in this case. But it doesn't mean that this one doesn't exist. It's still a minor structure, plus the alcohol. You could see here the equilibrium. It goes toward the higher pKa acid. And that's why you will see some reactions. Actually, it's much better to use a much stronger base, such as amide. So you can see here a cyclohexanone reacting with ethoxide. Once again, the pKa of that alpha carbon hydrogen is around 19. Once it gets deprotonated, you get the enolate, and this enolate plus the conjugate acid. 15.9 versus 19. You still have the equilibrium lies toward the left. So the problem with those reactions that do have the equilibrium lies toward the keto rather than the enolate, they tend to be much slower compared to the same exact reactions if they will take place in the presence of a stronger base. And here's how the equilibrium gets pushed to the right. When we have those reactions, even though the equilibrium lies toward the keto form, once they see an electrophile, you could see here clearly that it's an exothermic process that pushes it toward the alpha alkylation or the alpha acylation or the alpha halogenation product. And this is an example of a much stronger base than alkoxide. That's called LDA, lithium diisopropyl amide. When we have an N minus, whether it's an NH2 minus or an R2N minus, that's called an amide. The amide usually is generated through a reaction of a corresponding amine with butyl lithium, and the butyl lithium, the butyl group will grab a hydrogen that forms butane, goes from pKa of 40 to 50. That's how favorable the reaction is, and generates the strong base, which is in this case is the LDA. What do we do with the LDA? Again, we do alpha carbon hydrogen deprotonation. The same exact example we've seen with the alkoxide is the cyclohexanone has a pKa of 19. If we do this reaction in the presence of LDA, it's going to grab that hydrogen, it's going to form an enolate plus an amine, and that amine is pKa of 40. So you're going from 19 to 40. The difference between this one and the other, that this one goes from 19 to 16. So the equilibrium lies toward the left. But in the case of LDA, the equilibrium way more lies toward the right because of the higher pKa site being on the right-hand side. Another important aspect we need to understand that when we form the enolate, we have two resonance forms. We have the one that has the negative charge on the carbon, and we have the one that has the negative charge on the oxygen. How come there when an alkyl halide reacts with this enolate ion, the point of attack, it goes from the C minus or from the O minus toward the carbonyl, ending up basically with the alpha carbon attacking. Either of the two. How come we don't have the O minus grabbing that alkyl group from the alkyl X? Meaning, how come we do C alkylation rather than O alkylation? Well, the nucleophilicity usually prefers to have a larger atom. The larger atomic size atom, which is carbon in this case, is going to be a softer atom. And usually the softer the atom, the easier it overlaps with the vacant orbital of the electrophile. And that's important to keep in mind, that this has nothing to do with basicity. It has to do with nucleophilicity. The nucleophilicity, it corresponds to a large atomic size. Large atomic size means it's softer. The softer the atom, the easier it overlaps with the orbital of the electrophile. And that's why you will never see O alkylation. You will always see a C alkylation. And that's the more common outcome of those alpha carbon structures. Here's an example. We have a single alpha carbon hydrogen. On the other end, there is a phenyl. So there is only a one alpha carbon hydrogen. So that pKa is about 20. The LDA is going to deprotonate that hydrogen, is going to generate a C minus. And the C minus is going to do alkylation. So if it attacks a benzyl bromide, it's going to attack the carbon where the CX is. And that carbon basically is going to be attacked through an SN2 pathway. And you end up making the alpha alkylation product. And that's the first reaction that we do when we generate an enolate. Similar to that, alpha alkylation and alpha acylation and alpha halogenation is another structure that's not enolate. That's called the enamine. What's an enamine? Think of the enol. Enol, we have a C double bond COH. But what if I have C double bond C nitrogen? That's an enamine. So instead of enol, now we have enamine. The enamine has a two resonance form. Due to the lone pair being on the nitrogen, can delocalize to form an imine form. This imine, once it's getting formed, it's going to push that double bond to become a C minus. So those two structures are the resonance form of what we call enamine. Now we know that this is a major due to the fact that it has lower formal charges than the other. So that's important to keep in mind. Now this enamine, if we look at the electrostatic potential map for it, you could see the electron density is actually distributed on two sides of the molecule. One side, that's the nitrogen, and the other side, that's the carbon that's adjacent to that carbon attached to the nitrogen. So, which is let's call it the alpha carbon on that double bond. And that is the one that's going to be nucleophilic when we have an enamine reacting with an electrophile. Whether that electrophile is an alkyl halide or an acyl halide or halogenation. And the way it happens is basically the lone pair of that nitrogen will delocalize to form a double bond, and this C double bond is going to go with the electron density lies on that carbon, and that is the nucleophilic carbon that's going to attack the electrophile. Let's remind ourselves how we form the enamine. It's a reaction between an aldehyde or a ketone with a secondary amine. Why is it a secondary amine? Because if it's a primary amine or ammonia, it's going to form an imine. It's not going to form an enamine. So once you have that carbonyl of an aldehyde or a ketone reacting with a secondary amine, then lone pair on the nitrogen is going to attack the carbonyl carbon. It's going to give you the tetrahedral structure. That OH is going to be protonated to give you a good leaving group. And then the lone pair on the nitrogen is going to delocalize to form an imine. And this imine will be a protonated structure. So that's why it will be favored to go through the formation of the enamine. This won't happen if I would have a primary amine or ammonia. So what's going to happen when you get to this step, water will grab the hydrogen from the, not from this carbon, from the alpha carbon, and that is the one that's going to form the ene in the enamine. So you end up making the structure of enamine at the end. This is an important mechanism that we have to keep in mind. It happens only when you have a secondary amine reacting with an aldehyde or a ketone. And once we form that enamine, as I mentioned, the lone pair of the nitrogen is going to delocalize to form a C double bond N, and it's going to push that pi bond to attack the electrophile. And the alpha carbon will be the one that's going to be alkylated or acylated or halogenated. And look at this chemistry. And somebody might say, okay, if it gives you the alpha carbon to be negatively charged, why wouldn't just stay in that form? Well, this happens only when you have an electrophile. You have to have an electrophile in order for the lone pair of the nitrogen to delocalize to form a C double bond N and push the pi bond to be a C minus. If you don't have an electrophile, obviously the stable structure is the enamine that you see in front of you. So once you have that alpha carbon carrying the negative charge, it's going to attack the carbon of the CX. That's an SN2 reaction. And once you have the outcome, which is the alkylated iminium salt, in presence of H3O+, this is a reaction we learned actually in the amine chapter and in the aldehydes and ketone chapter. When you have an imine, usually it's hydrolyzed to the corresponding carbonyl structure. So when you have an imine or an alkylated iminium salt in the presence of H3O+, what's going to happen that this C double bond N becomes a C double bond O. And of course, it kicks off the amine as a protonated as secondary amine. So this is important to keep in mind that the enamine with an alkyl halide or an acyl halide or halogen, the alpha carbon to the nitrogen C is the one that's going to be attacking that electrophile. You end up making the alkylated or acylated or halogenated iminium salt, which upon hydrolysis will give you the corresponding ketone. You could see here an acyl halide. So the acetyl chloride reacting with the enamine is going to do the same chemistry. So instead of attacking an RX SN2, it will attack the acyl. That's called acyl substitution, nucleophilic acyl substitution. So this nitrogen lone pair will still be delocalizing to form a C double bond N. That's the imine, and then this double bond is going to be carried over to that alpha carbon to attack the carbonyl carbon, and that's give you the tetrahedral intermediate. The O minus will come back and restore the carbonyl, and that kicks off the Cl. So you end up making an acyl alpha substitution. So that upon hydrolysis will give you the ketone structure or the beta diketone structure in this case. So that's how important the enamine is, that it does similar chemistry to the enolate structure. So you can think of it this way, that if I have the cyclohexanone, if I have a cyclohexanone and I want to do alpha acylation, there is a chance that I will end up making multiple acylated structures, or I may end up making lower yield of a monoacylated structure. So the better route is to form the enamine, and that's very easy. All what you need to do is to react the cyclohexanone with the cyclohexanone with the secondary amine that will give you the enamine, and then the enamine you could do the alpha carbon chemistry with it and then hydrolyze it back to the carbonyl structure. So we learned how to do alpha alkylation of enolates, alpha acylation of enolates, alpha alkylation of enamines, and alpha acylation of enamines. We could also do alpha halogenation of enolates and enamines. So here is an example of a ketone structure. In the presence of a hydroxide and halogen, you're going to generate the deprotonated structure, that's the enolate, and that enolate will attack the halogen to give you the alpha haloketone plus X minus plus water. So this can be done in the presence of acid or in the presence of base. So it could be acid catalyzed alpha halogenation of ketones or base catalyzed alpha halogenation of ketone. It's important to keep in mind that if I have the base catalyzed alpha halogenation, there's a chance that I might end up getting multiple halogenated steps if I have enough of the base. So the acid catalyzed alpha halogenation become a safer choice if I have more than one acidic alpha hydrogen. So the process is very simple. The OH minus grabs the hydrogen, it gives you the enolate, and the enolate, whether you have the O minus one or the C minus, you could use either of the two to do the arrow pushing. If you decide to use this, the O minus will make the C double bond O, and the C double bond C will attack the halogen to give you the alpha halogenated product. And that's the problem with having more than one alpha carbon hydrogen. If you have two, you will substitute the first one, and you will go on with the second one being deprotonated because it becomes easier. Think of it, you have a deactivating group. It makes that acidic hydrogen even more acidic than the previous ketone. So that's important to keep in mind. This step becomes easier than the first halogenation step. And once you grab that hydrogen, you're going to form an enolate. That enolate attacks another molecule of halogen, and that gives you a halogenated product. If there is a third, it will go through a third deprotonation to give you the third alpha halogenation as well. So this is the problem with the base catalyzed alpha halogenation, that you may have no control over how many halogenated steps be happening as long as you have enough base and as long as you have enough halogen. And it's hard to control, even if you have one equivalent of the base and one equivalent of the halogen. That's why it's safer to do the acid catalyzed, and we'll see that in a second. Here's the haloform reaction. That's based on the same alpha halogenation that we looked at. The haloform reaction is a qualitative test that we use for methyl ketones. What does a methyl ketone mean? Methyl ketone, when you have a carbonyl attached to a CH3. And when you have that, the haloform test becomes a qualitative test to do to confirm whether we have the alpha or the methyl ketone or not. How it happens, you have excess of the halogen and excess of the hydroxide. So you end up basically deprotonating the first one, then doing halogenation, deprotonating the second, doing a halogenation, deprotonating the third, making a halogenation. So you end up making a CX3, and X being a Cl or a Br or an I. So in the case of Cl2, you have the chloroform test or the chloroform reaction. In the case of the Br2, it's a bromoform. And in the case of I2, that's the iodoform. So if you hear those tests, iodoform, bromoform, or chloroform, you need to think of the methyl ketone being tested. Does it exist in the structure? If it does, it will give you a positive test. And we'll see what the tests mean in this case. So once you form that trihalomethyl ketone, in the presence of OH minus, which you still have excess of, it's going to attack the carbonyl, and it's going to kick off CX3, and that's going to give you the carboxylic acid plus CX3 minus, which will grab the hydrogen from the carboxylic acid to give you the carboxylate plus the haloform. This is a yellow precipitate. So when we do the haloform reaction, and if we see a yellow precipitate, whether it's a bromoform or chloroform or iodoform, we know that we have a methyl ketone. And that's the indicator that we usually look for when we do the haloform reaction. And once again, it's a triple halogenation steps. So the first step, usually the first hydrogen to be deprotonated, and then halogenation, then the second hydrogen to be deprotonated, then a halogenation, and then the third time you do deprotonation and then halogenation. So you don't think of the three hydrogens being deprotonated at the same time and the three halogens to be added at the same time. That doesn't happen. And here's the detailed step of the formation of the carboxylate. So the OH minus attacks the carbonyl carbon, kicks off CX3, and the CX3 minus goes back and grabs the hydrogen from the carboxylic acid. It's basic enough to grab the hydrogen from the carboxylic acid, so you end up making a carboxylate plus the halo form. And as I said, in the case of Cl2, you form a chloroform. In the case of Br2, you form a bromoform. And in the case of I2, you form iodoform. And that refers to the HCX3. This is the iodoform. So we can see excess iodine and hydroxide. That's going to end up making a Ci3. And that goes through the same step that we've seen previously to end up making the carboxylate. In this case, it's the benzoate, since we're starting with the acetophenone, plus the HCI3. And that's a yellow precipitate, as I mentioned. So this is a reaction that's being asked for. So you could basically, to show the mechanism, how it's done, the alpha hydrogen to be deprotonated in the presence of base to give you the enolate. Always draw both structures, the carbanion and the enolate, and that will always be referred to as the enolate ion. And it's a resonance, not an equilibrium. Don't mix this with the tautomers of keto and enol form. These are tautomers, but this example, it shows you basically enolate that generate from resonance phenomena. And once you have that, you end up attacking the halogen, and that gives you the monohalogenated structure, or alpha halo ketone. Here's a safe way of doing alpha halogenation. To prevent multiple halogenation, we do the acid catalyzed alpha halogenation. So in the presence of an acid, that it's going to protonate the carbonyl first. We're going to see the mechanism in a minute. So you can see here, the outcome is the same exact thing we do previously, which is the base catalyzed alpha halogenation. If you have two equivalents of the halogen, that's when you do a second halogenation. So in the case of one equivalent, you end up having monohalogenated product. In the case of two equivalents of the halogen, you end up making dihalogenated structures. So the determining factor here is the amount of halogen being used. In the presence of a base catalyzed alpha halogenation, we can't control the reaction. Whether we use limited amount of base or limited amount of ketone, we end up not being able to control the halogenation step. So that's why acid catalyzed alpha halogenation becomes. We're not saying that the base catalyzed alpha halogenation is not useful. It is, because sometimes you could control the reaction, but when you have sterically hindered ketone structures that do have alpha carbon, that's not that easy to deprotonate. And when you use a bulkier base, such as LDA, you may end up actually doing monohalogenation rather than multiple halogenation. But this is an example we could see here that we can do acid catalyzed, and the chemistry, it goes through the enol formation. So the carbonyl gets protonated first and end up making the enol. And then this enol goes through delocalization on the oxygen back to the C double bond O. And this C double bond C is the nucleophilic part of the molecule to attack the halogen. That gives you the alpha halogenated carbocation. And this ends up basically losing the hydrogen to restore the carbonyl. And that ends up giving you the alpha haloketone. The same outcome we do get when we have base catalyzed alpha halogenation. But in that example, we generate enolates. In this alpha halogenation of an acid catalyzed medium, we generate the enol rather than the enolate. See here an example of a cyclohexanone reacting with Cl2 in presence of an acetic acid. To give you basically 2-chlorocyclohexanone. And again, the mechanism goes through the protonation of the carbonyl oxygen first, gives you the protonated ketone, and this ketone is going to end up giving you the enol form. And that's important to generate the enol when you have an alpha or acid catalyzed alpha halogenation. And once you have that enol, the lone pair on the oxygen restores the carbonyl, and that C double bond C, it attacks the halogen to give you the alpha chloroprotonated ketone, which goes through the last step of deprotonating that hydrogen to end up giving you the alpha haloketone structure. So that's what you do when you have alpha halogen acid catalyzed alpha halogenation or base catalyzed alpha halogenation. Now, some structures that do have alpha carbon, they happen to be carboxylic acids. So if you react this carboxylic acid with a base, the first proton to be deprotonated is going to be the carboxylic acid. So that can become useless to do. So in the case of a carboxylic acid that does have an alpha carbon acidic hydrogen, then we're gonna need to think of the Hell-Volhard-Zielinski reaction, HVZ, Hell-Volhard-Zielinski reaction. This reaction consists of the following: carboxylic acid reacting with Br2 and phosphorus tribromide. What are these two do? It's a complex that generates the acid bromide, and then it does the alpha halo formation, and you end up making the carboxylic acid, recovering it back by hydrolyzing the acid bromide. So we're going to see the mechanism in a minute, but it's a two-step process. The first step is Br2 PBr3, and the second step, which is a must, is H2O. Because if I don't have the second step, which is H2O, I'm making not just the alpha carbon brominated, but I will end up making the acid bromide, not the carboxylic acid. So we can see here an example: butanoic acid. It's not wise to use OH minus and Br2. It's not wise to use H plus and Br2. You need to use the Hell-Volhard-Zielinski condition, and that basically requires the use of Br2 and PBr3. It's going to give you the acid bromide and carbon brominated. And one H2O step, hydrolysis of the acid bromide, gives you the carboxylic acid. And this is basically the detailed mechanism. Step number one will be the formation of the acid bromide. The oxygen attacks the phosphorus, kicks off one of the Br, and the Br comes back and attacks the carbonyl to end up making the acid bromide. That's the first step. And the acid bromide does have basically the keto enol form. This alpha carbon, it basically getting picked up by the medium to form a C minus. That C minus forms a C double bond C, opens up that O minus to grab the hydrogen back from the medium. So you have more of a proton transfer. So you go from a CH to an OH, but that will be on the expense of the C single bond H to become a C double bond C. So that's important to keep in mind, that you only have a double bond that's either between the C double bond C or the C double bond O. Of course, this will be the major, because the keto form is usually more stable than the enol form. The C double bond O, it's much more polarizable and much stronger than the C double bond C. And that's why the structure prefers to stay in the keto form rather than the enol form. But once we have the enol form getting generated, you could see clearly that the chemistry is going to take place from the C double bond C. The lone pair delocalizes to form a carbonyl, restoring the carbonyl, and that C double bond C attacks the halogen to give you the alpha carbon halogenation, or the alpha carbon bromination in this case. And the last thing to do is the Br minus grabbing that hydrogen from the carbonyl oxygen to give you the alpha bromo acyl bromide. So it's a two-step process. The first step is the formation of the acid bromide, and then the second step would be the alpha carbon being brominated once you form the enol. And this is a required mechanism. Make sure that you go over it to not just understand how the arrow pushing is also to be able to draw the intermediates of this mechanism. And what's going to be next is the more reactions of alpha carbon condensation with a carbonyl of an aldehyde or a ketone, that is aldol condensation. We will see the condensation esters, and that will be the Claisen condensation. We will see the 1,2 and 1,4 addition, and some more reactions that are all involve the formation of enolates.